start with some background knowledge and then follow our discussion. Follow our discovery, sorry. So as you know, mechanical energy is a green research energy resources. So large mechanical force like a strong wind, waterfall have been used for power production for many years. Recently, there are lots of interest in using small mechanical energy for generating electricity. So the main purpose for this is because of the booming of personal electronic devices. So they need regularly chargers. So if we can have some energy harvester to segregate the surrounding energy for charging these personal devices, it will be very handy. So another reason for this is because that's small mechanical to electricity generator could be used for development of self-powered sensor network. So for the development of the energy harvester, lots of principles have been used. So include the electromagnetic principle, piezoelectric principle, and triple electronic principles. However, most of the energy generator generate AC power. The problem for the AC power is if we want to use multiple devices together, they need each power generator need a rectifier, because without this, the signals, the output may cancel each other to reduce the energy production. However, the use of the rectifier may consume the energy. It also makes the whole device very complicated. So it will be ideal if we use a DC power generator. So our finding may be a solution to solve this problem. So this is our earliest finding. We found this by chance in our laboratory. Initially, we want to use PVDF, elastomer nanofiber, as an active material to generate electricity and compression. Because this material is not conductive, they have a large internal resistance. So to reduce that, we try to use a conducting polymer to improve the conductivity. So we use a solution to synthesis conducting polymer, and in the meantime to add nanofibers in the solution. So by changing the concentration of pyrrole, we found the nanofiber, the coated nanofiber, can have different output. For example, for the low loading of PPy, still have a AC power output. However, when the loading is high, so the power become DC. So then we conduct a series of the investigation and trying to find out what happened for this device. So eventually we found it comes from two reasons. One is the use of conducting polymer PPy. Another is mistakenly we use two different metal as electrode to form a device. So like this. So one layer, one electrode we use gold, another we use aluminum. But the nanofiber may not be necessary for this energy conversion. So we come back to understand what happens if we just use conducting polymer and two metals. So this is our improved experiment. So we prepare a polypyrrole dense disc by compressing the powder together. So that's like a round disc, a sandwich between two metals. One is aluminum, another is gold. So on the compression, so you can see the device indeed generate DC power. So each peak consists of a compression and decompression action. So there's many peaks come from many cycles of compression and decompression. So the output is about 0.7 volt. For the device, for the disk around 13 millimeter in diameter, the thickness is 1.44 millimeter. So that's conducting polymer device can generate voltage output. The current output is about 300 microamps. So if we change the stream models, we found something more interesting. So the left up result shows when the strain increase and decrease in the same speed for several different cycles, the electrical signal generate in a way similar to the strain change. However, if we use other strain model, like a suddenly increased strain to a certain level, and then maintain the strain for a certain period of time, and after that suddenly release the strain until next cycle. So we can see the electrical signal generated in different way to the conventional piezoelectric device. So for our device, once the electrical signal reach to the highest point, it decay very slowly. However, for the conventional piezoelectric device, so when the output reaches to the highest value, it decay very rapidly, sharply reduced to zero. So that means our device have more energy than conventional piezoelectrical devices. And if we change the sample size, for example, changing the working area, but maintain the disk thickness, we typically found the voltage doesn't change much, but the current changes very largely. So this result shows with increasing the sample size, the current increase. But if we increase just increase the thickness, we found that the voltage still maintain the same level, but the current slightly reduced. So this reduction come from the increased internal resistance. So we also tested the control devices. For example, if we use gold as an electrode on both sides, we cannot get any signals so during from the device. But if we use aluminum as the electrode on both sides, we get a complicated output like this. This include both positive and negative signals, but the output is very low, very small. So in literature, we can find conducting polymer PPy from a Schottky junction with aluminum, but it form a ohm conductor with gold. So therefore, our device should contain single Schottky junction. So if we test the IV curve, we can typically find a rectifier effect in the device, and the compression, the rectification rate increased. But for the ohm conductor device, it's made from gold electrode on both sides. So it looks like just like a straight line. And the compression, the current increased. This means the PPy conductivity is improved and the compression. So based on the classical equation, we can calculate the Berry height of the Schottky junction. So this is the calculation equations, and we found on the compression, the Berry height is reduced for our device. So based on the experimental result, we propose energy conversion mechanism here. For the Schottky junction, PPy, when PPy contact with the aluminum, they form a Schottky junction because PPy is a p-type semiconductor. So some electron move from aluminum to PPy layer, and the holes move from PPy to aluminum. So that's reach equivalent. So on the compression, because the very high reduction, some electron move back to the aluminum layer, creating a difference, electrical potential in the interface. And because the ohm contact between PPy and gold, and we can test this electrical potential on the two electrodes. So the right cartoon shows the energy conversion process, so like this. The electron actually pumping out from gold to from PPy actually to aluminum, and then return to the device from the external circuit. So we also found other conducting polymer like polyaniline, polysiphon have a similar property as long as it can form a Schottky junction with metals. So this Schottky junction can generate a DC power under compression. And the voltage output is really dependent on the work function of the materials. So using polyaniline, we can also understand how the dopant influence the energy conversion, because polyaniline can be doped and de-doped and redoped by different acid dopant. So we use the same batch of polyaniline and de-dope that, and after that we can redope the de-doped material with different acid and prepare the disc. The disc like this, they contain different acid dopant. So we found that the acid indeed, the dopant indeed influence the energy conversion ability. The one with the smallest size can lead to larger energy conversion ability. The reason for this is because a smaller dopant gives sufficient dopant levels, and it also reduces the very high in the compression state. So we also use other materials to dope conducting polymer. For example, nano carbons like a carbon nanotube, graphene oxide. We found only small contents of this material can lead to large improvement in the current output. For example, here we just add 1.6% graphene oxide to polypyrrole. It lead to 6-time improvement in current output, but the voltage still maintain the same level. The reason for this is because graphene oxide can improve the conductivity of PPy and also reduce the very high and compression state. So not only Schottky junction, so we've also found if conducting polymer can form a p-n junction with other semiconductor like inorganic oxide. The p-n junction also can be used as a generator. So here is an example. We use tin oxide and the PPy to form a p-n junction because tin oxide is an N-type semiconductor. So the device can generate a DC power and the compression. The voltage output is around 0.25 volt. The principle is very similar to the Schottky junctions. So here are more results that come from different p-n junctions. So you can see the voltage output varies depending on the material used, the p-n junction material, the semiconductor used. So more recently, we found if we use a PPy-coated non-woven fabric as an active layer to make a Schottky junction, so this device can generate a higher voltage output. So it can reach 3.27 volt, and the power can improve by 3.4 times high. The reason for this is because this device involves two energy conversion principles. One is Schottky piezoelectrical conversion. So this can happen on the top layer of fabric. So there's a PPy-coated fabric constantly contact with the aluminum electrode. So on the compression, they generate energy, DC power. And others for the PPy-coated fiber underneath the top layer, they still have a chance to contact with the aluminum surface that's under compression. So this causes triple-electrical energy conversion. The triple-electrical effect contribute to larger voltage output. So we also prove the energy generator can be used for many different applications. For example, we can make a button-like device and use the device as an energy harvester to light up LED, for example, or we can use it as a strain sensor to sense the force, the compression forces, like this. The energy can also be stored in capacitor for further use, for example, to drive motors, electrical motor, heaters, and also electrical cooler. So we also embed the device into shoes for harvest working energy. So to prove the simple connection, so we prepare multiple devices and link them together. So in this case, we just need to pay attention to the polarity, make sure the polarity in the same direction, and then we link that either in parallel or in serial to get a larger power. So to prove this, we prepare a smart tile prototype. This consists of a non-button-like device. They are connected in serial. So you can see just a step on the tile, so they can light up LED, and can also be used for other purposes, like testing the speed and also monitoring, counting the steps. So this work is a teamwork. It's done experimentally in my group. It's by PhD student, research staff. It's also we also involve lots of collaboration in this area. This include our research unit group in USA and also two research group in China. So the research also receive funding support by Australian government through a discovery project. So we have a website, group website. If you are interested in our works, please visit this website. You can find more information about our work. And finally, thank you very much for your time.